Today you're welcome to waidsumacademy. Today we're still on electricity, current electricity, and this is the third part of the current electricity. The part one was electrostatic, and part two was basic current, charge, motion, charge in motion, which we call current, and we differentiate conventional current, direction of the conventional current. We said conventional currents, they flow from the positive uh, terminal of the battery to the negative terminal, and we say the electrons, they flow from the negative terminal of the battery towards the positive in the circuit. Okay, so we've also looked at the basic current. We define current, and we looked at the components that are used in electric circuit. We define some of them, we drew them, we show how they look and their symbol and their functions. We've looked at all of this. Okay, so today we've defined current, we looked at current. Now we're going to look at potential difference. And there's a very strong relationship between potential difference and the current that flows in a circuit. Remember, we say current is invisible. You don't see current. Current is invisible. It is the electricity that you don't see. But what you see is the potential difference. What you see is the voltage, the potential difference. The one that glows in the bulb. When you put up your bulb, it glows, it lights up. That one is the voltage, is the potential difference. Okay, but the current that is flowing in the wire that comes to the bulb, that lights up the bulb, you don't see it. Okay, it's invisible. So the potential difference is same. It has similitude with electromotive force. Electromotive force is the potential in the battery. The electromotive force is the potential in the battery. But the potential difference, the one we call the potential difference, is the potential in the component, in the circuit component. So I'm going to show you this from a diagram. I'm going to show this from a diagram. Let's say, for example, we have, just a minute. Okay, let's say, for example, we have a circuit. Okay, physics. It's too weak. Physics. Okay, let's say, for example, we have a circuit. We see on PD, we're doing PD, potential difference. Okay, so let's take that potential difference. Let's say if we have a circuit, and the circuit has a battery, right? Every circuit you need a battery, and then this is our battery, for example. Okay, we draw a simple circuit. We put our bulb here. This is our bulb. This is just the symbol for a bulb. Okay, and then we take it to, let's close it. Let's assume the switch is already closed. Let's assume the switch is here and it's already closed. So it's a closed circuit. So current is flowing. This is the longest arm. This taller arm is called the positive side of the battery. Why this short? You know, you have long, short, long, short. Okay, each of the long one is the positive. The short one is, this short one is negative. This long one is also positive. This short one is negative. Okay, so this is a battery. Now the PD here, this is a component. This is a cycle component. This is not. This is the source. We call this one the source of the electricity. The battery is the source of the energy. The battery is the source of the energy, right? So this battery is the source of the energy. So this source is the whole thing starts from here. The whole thing starts from here. So although you may call it a component, but it's the source, the power source. This is the power source of the energy, source of energy. So the battery is the source of energy. Now this is where we have the electromotive force. Is the source of energy or source of the electricity, source of energy. Okay, the battery is the one that produces the energy and the charge that is being driven around the circuit. So source of energy is here. So the force also is coming from here. The force that drives the charge around the circuit is coming from the battery. That is driving the charge around the circuit is coming from the battery. Now when we connect a voltmeter across the battery, we measure the EMF. So the reason why I'm bringing you here is that we want to talk about the difference between the EMF, electromotive force, and the PD. Now, PD is the one we have across the circuit component. The PD, when you connect a voltmeter, you know I told you to connect a voltmeter, you must make it what? These are two terminals where you tie your wires. You must make it parallel. You must make the voltmeter parallel to the component, to whatever component you are measuring. So it's different from ammeter. In the case of ammeter, we make it series. If it's ammeter now, I'll just put it here. I'll put the ammeter, I'll make it series with the bulb. But for voltmeter, you have to make it parallel to the bulb. It has to be parallel to the bulb. So here, we are measuring the PD, or what you call the voltage. Here we are measuring the PD, potential difference, the PD. In any component, whether it's a resistor, if we have a resistor here, same thing. We're going to be measuring the PD, okay? If we have a bulb here, you are measuring the PD. If you have a resistor here, you are measuring the PD. So here we are measuring the PD or the voltage. The PD or the voltage. The voltage is the name we call potential difference. It's also a name we call the electromotive force. Okay? So we are measuring the PD across the components, across this bulb. We are measuring the PD across this bulb. Okay? But when we want to measure the one across the battery, we don't normally call it the PD, although it still is, but it has a specific name. So here, when we measure this one, we call it what? We call it electromotive force. Across the source, if you are connecting the voltmeter across the source, what we measure, we call it the electromotive force. We call it what? The electromotive force. Hence, we will define electromotive force. We will define it as the energy needed to drive the charge around the circuit. Okay? You connect a voltmeter here as well. And we can define the electromotive force as the energy needed to drive the charge around the circuit. The energy needed to drive the charge around the circuit. While the PD is the voltage across the bulb. However, they're kind of same thing. But here, across the battery, which is the source of energy, we call it electromotive force, EMF. We call here EMF. The voltage or EMF. Okay? So I'm trying to show you the difference because in the exam, they might ask you to differentiate between EMF and a potential difference. What's the difference between an EMF and a potential difference? One of the significant differences is that an EMF is measured across the battery, across the source of energy that drives the charge around the circuit. While potential difference is measured across every other circuit component, like the resistor, like the bulb, like the filament lamp, like the fluorescent lamp, and any other circuit components that we have, or even across a conductor, any conductor, like the wire itself. So this we call the PD, potential difference, or the voltage. But the EMF is the voltage that is measured across the battery. We call it electromotive force. It's a kind of force that drives the charge. It's called electromotive force because it's an electrical force and it's in motion. It drives the charge around the circuit. Okay, so I hope this is clear enough. Now let's properly show the concept. But in doing that, let's listen to this tutorial for like less than 5 minutes or 2 to 3 minutes, and then we will continue our game. So just pay attention and see.
This video is on the topic of potential difference and electromotive force. We know that electrons are negatively charged, and so they are attracted to the positive terminal of the cell. We also know that like charges repel. Therefore, the negatively charged electrons are repelled by the negative terminal of the cell. So what happens when the electrons pass through the cell? How do they get from the positive terminal to the negative terminal? How do they overcome the repulsive electrostatic force? Remember, for an object to have a positive charge, there has to be a lack of electrons. Positive charge cannot move because the protons are in the nuclei of atoms. Only electrons can move around. So to get electrons flowing in the circuit to move from the positive terminal to the negative terminal, work has to be done on the electrons to push them towards the negatively charged terminal, and that requires energy. That energy comes from the chemical store of the cell. The cell is the driving force that makes the charge flow. Without this, there is no current. So energy is transferred into the circuit from the cell, and energy is transferred away from the circuit by the components, such as a lamp. Therefore, it can be said that energy is transferred from the cell to the components. Electromotive force is the work done by a power source in moving a unit of charge around a complete circuit. That's the work done, or energy transferred, per unit charge. Potential difference is the work done by a unit of charge passing through a component. That's work done or energy transferred per unit charge. Both are measured in volts. Things get a little more complicated when you get to A level, but for now they are essentially the same thing, numerically speaking. The difference is that EMF is the energy transferred to the circuit, and potential difference is the energy transferred away from the circuit. You only need to know these equations if you're studying the extended content. We know that an ammeter has to be positioned in series so that the charge flows through it. An ammeter counts the amount of charge passing through it per unit time to give a value for current. A voltmeter works very differently. Let's say that the potential difference of the cell here is 1.5 volts. That means that the positive terminal has an electric potential of 1.5 volts and the negative terminal is 0 volts. So this wire, up until the component, is 1.5 volts. And this wire, up to the component, is 0 volts. A voltmeter measures the potential difference, or the difference in electrical potential, between 2 points in the circuit. Think of the branches or wires on either side of the voltmeter being like arms grabbing onto 2 different points in the circuit. It measures the potential difference between these 2 points. For that reason, a voltmeter has to be positioned in parallel to the component it's measuring. It has to be connected to 2 different points. Let's apply this understanding to an exam question. Which row of the table correctly shows the readings from the voltmeters in this circuit when the cells in the battery are 1.5 volts each? Okay, so we know that the potential difference of each cell is 1.5 volts, and we have 2 cells in the battery. That gives us a total potential difference of 3.0 volts. There's a very easy way to figure out the potential difference at any point in the circuit, and that is to colour the branches. So if we follow this branch at 3 volts all the way to the components, and if we follow this branch at 0 volts all the way to the components, then we can clearly see that voltmeter 1 reads 3.0 volts, voltmeter 2 reads 3.0 volts, and voltmeter 3 reads 0 volts, nothing. Therefore, the correct answer is B for 1 mark. A couple of things to pick up on here. Firstly, voltmeter 3 reads 0 because it's positioned in series. But even if it were positioned in parallel, we can see that there is no difference in electrical potential in this branch. Both arms of the voltmeter would read the same 0 volts. And secondly, what would this section be between the resistors? Assuming that the resistors are equal in value, then the energy transferred to each one from the battery would also be equal. Therefore, half of the energy would be transferred to the first resistor and half the energy would be transferred to the second resistor. If we were to add a voltmeter in parallel across each of these resistors, we can clearly see that they would both read 1.5 volts. In summary, the cell has 2 roles within the circuit. Firstly, the electromotive force. The cell drives the current around the circuit by doing work on the electrons to overcome the repulsive electrostatic force. Secondly, the potential difference. The cell transfers energy into the circuit and the components transfer energy away from the circuit. So it can be said that the cell transfers energy to the components. Voltmeters measure the potential difference between 2 points in the circuit, and to do this, they have to be connected in parallel. And finally, remember that you can easily find the potential difference at any point within any circuit by coloring the branches from each terminal of the cell, battery, or power source. Don't forget to check out all our other fantastic revision resources here at Save My Exams.
Okay, so we've just seen a bit overview of what we have regarding the difference between electromotive force and potential difference. Just like we've stated earlier, when we stated, we said the electromotive force is responsible, is the force or the energy that drives the charge to the rest of the circuit. It drives the charge from the source, the battery, to the other part of the circuit, to the components, to the rest of the circuit, okay? While the potential difference, the voltage in the components, drives the energy back to the cell, because this energy is in a continuous loop, okay? It's driven from the source, which is the battery, and it returns back to the battery. So it's driven from here, and the potential difference in the components continues to drive it back to where it's coming from. So the source EMF drives the charge round to this component, and then from the component, the PD or the voltage here continue to drive this back to the source. So these are basic things that at this level, in lGCSE, we put both the EMF and the potential difference to be almost same thing, but in A-level studies, the difference will be explained. But at lGCSE level, we assume them to be same, that they are both voltages. But there is slight difference for us to study at higher level. Okay, at higher level, either at A level or in the university. So we say that electromotive force is defined as the electrical work done by source in moving a unit charge around a complete circuit. The electrical work done, you can say work done, or the energy that is being there transferred. We can say it is the work done, the EMF. We can simply say the EMF is the work done or the energy that is being transferred. So we can simply say EMF is work done. Okay? The work that is being done is equal to the work done or energy transfer in driving a charge around a circuit, a complete circuit. Okay? Work done, the work that is done, or the energy that is transferred. Remember, work done and energy transfer, they are same, they are similar. Okay, because it is the amount of energy that has been transferred that determines the amount of work that will be done. Okay, the work done or energy transfer in driving a charge around a circuit, or energy transferred in driving a charge. You know, it's all about the charge. The movement of a charge, remember, is called current. Okay, the charge would be stationary in the battery, okay, in the form of chemical energy if it's not driven around. So this charge needs to be forced out of the battery to move and travel. So when it's moving, it becomes current. This charge, when it's moving, it becomes current. So we say the energy that has been used to transfer the charge, to force the charge out of the battery, is called the electromotive force. So it is the work done, energy transfer, in moving a charge around the battery. In moving a charge. So the big deal, or what is at stake, is the charge. What is at stake is the charge. So is the energy transferred or the work done in moving this charge. So I can even put a quotation mark here to show this is the big deal. You must mention this in your definition. In moving a charge round round a circuit, round a electrical circuit, round an electrical circuit. So I'll just write circuit for simplicity. Round a circuit. Okay, circuits are usually electrical. So to make it simple, we just write circuit. So the work done per unit time or per charge. So if we're defining this, our EMF, we're putting it in formula form, the electromotive force is equal to, mathematically written as the work done, so we can write W, or E, the work done, or the energy that has been transferred, or that have been used to move this yungu, to move this quantity away, right? The energy that has been transferred to move the charge, to drive the charge. So we can simply say it is work done over charge. Okay, the EMF is the work done over charge. On the other hand, what about the potential difference? What about the potential difference? The PD, okay, we use the abbreviation. Let's select a different coloration. The PD is the energy that was used to transfer the charge now from the component to the source. Okay, the PD is the energy that was used to transfer this charge from the component to the source. Okay, we're coming back to write that definition. So let's first of all continue the explanation on electromotive force. When we're done with that, then we face the PD, potential difference. So electromotive force, EMF, is measured in voltage, meaning the unit is volt. So whenever you see the value here, the voltage here of the battery is the EMF. It's actually the EMF. Okay, it's measured, the unit is in volt. The unit of EMF is volt. The unit is volt. So we can say unit equal to volts. And remember, unit of voltage is volt. You remember we say both EMF and PD, they are actually voltage. They are actually voltage. Okay, so we move on. EMF is the voltage supplied by the battery or by the power source. You see, it's the voltage. The EMF is the voltage that is being supplied by the power source. The power source is the battery in this regard. Okay, the voltage supplied by the power source. And it depends which value it is, and that's the voltage. If it's 12, that means the voltage is 12. If it's 24, the voltage is 24. If it's 6, the voltage is 6. So the voltage that is supplied by the battery is what we call the EMF. So the definition of EMF is simply mathematically, just like we've written, that EMF is the work done or the energy that has been transferred in driving a charge around the circuit. So EMF is equals to the work done over charge. Work done over charge. So E in this formula is the EMF, electromotive force. W is the energy supplied to the charges from the power source. Either you call it energy supplied to the battery from the power source, or the work that is done. That is done when the energy has been expended or has been transferred. Okay, so now here is a basic questions that they can easily ask you to throw you off balance, to see whether you know exactly what you're doing. Okay, here is a question. For example, we say electrical quantity and electromotive force. Now we say, from the list of units below, select the appropriate unit of electromotive force. Okay, in the exam. These are in lGCSE exams. Select the appropriate unit of electromotive force. You say ampere. No, ampere is for current, right? So anyone we mention, we should say what it stands for, what unit it is. Joule is for energy. So Joule is not for electromotive force. Watts is for power. Watt is not for electromotive force. Volt, yes. Volt is the unit of electromotive force. So electromotive force, remember we say, is the name that is given to the potential difference or that is given to the voltage of the power source in any circuit. The name that we give to any voltage in the power source. The name we give to the voltage in the power source, or yes, the name we give to the voltage in the power source, or the PD, the potential difference in the power source, is what we call the electromotive force. So it's still voltage, okay? So the unit is a volt. The unit is a volt, okay? So I think we pause and listen to this tutorial again before we continue, before we move on to the potential difference.
here's a question for us to look at. So let's start by reading through it very quickly, or even very slowly.
Okay, let's move on. We've answered that question. So let's just move on. Now let's go to the PD, potential difference. Okay. Okay, what is PD? A PD is the work done by a charge when it's moving across a component. Work done by a charge when it's moving across a component, a circuit component. Work done by a charge. So when the charge, the charge that is traveling is current. So when the current moves across the component, then work is done. That work done is called that glowing you see when the bulb glows. That work that is done is called the PD. The PD is the work done by a charge when it's moving across the component. When it is moving across the component. Which component? Maybe a resistor. Let's show a circuit component. A resistor this time around. So we draw a circuit component. So technically the PD is same. The formula is same because it's also work done. So work done is either we use W or we use E over charge. So the formula is technically same or numerically same. But technically, the explanation for all there is a difference technically, which you will do at A level. But for this level, they are numerically same. Now, we said the unit is also volt. Unit is a volt for PD. So both PD, voltage, and EMF, their unit is a volt. Potential difference, electromotive force, and voltage, their unit is a volt. Their unit is a volt. Okay, now let's take a look at a circuit component and show where we have a potential difference. Let's take a look at a circuit component and show where we have a potential difference. Let's say this is our source, power source, the battery. And then we have a resistor here. We've drawn the various circuit components in our previous class. We've drawn various circuit components in our previous class, right? So this is a resistor. Let's say we have resistor 1, and again we have another resistor in this circuit. So we have two resistors. So we have two resistors. Okay, this is our circuit. Let's say this is our circuit. So we can call this R1. The first resistor, we call it R1. The second resistor, we call it R2. Now you can see that both R1 and R2, they are in series. Okay, we'll talk about the arrangement when we start doing resistors. It's another subtopic. Okay, in this, after potential difference, we'll be treating resistances. So this one, they are in series, meaning they are on the same straight line in the loop. They're together in the same straight line on the loop, okay? So we have two components. Here, if we connect a voltmeter, here, you know that the voltage in each of the devices is different. The same current flows in these two devices. The current that flows here in this wire that is coming from here, this current that is coming from here is the same current that goes in here, and is the same current that leaves this resistor 1, R1, that enters this resistor R2, and the same current that returns back. Remember, it's just the charge. Charge in motion is what we call current. So it's the same current that comes back to the battery, okay? So same charge that comes. So in series, the same current flows in the different components. the same current flows in the different components. You have to keep this in mind. You have to bear this in mind. In series, the same current flows in the component. However, the voltage is different in different components. The voltage here is different from the voltage here. So if you want to find the voltage in R1, we have to connect a voltmeter parallel to R1. If I want a singular voltage here, okay? So I have to connect a voltmeter. Across R1 to find my V1. So I can find the first voltage called V1. Okay? These are terminals. You see, I always put a point before I connect. That's where you terminate the wire. Okay? So the voltage is different in the different components. The voltage are not same in series, but the current flowing through the components, circuit components are same. The current that is flowing through the circuit components are same. However, the voltage in series are not same. So the voltage are different in the different circuit components in series circuit, but the currents are same. So here we have V2. Here we have the second voltage called the V2. Okay, so this is how we measure the voltage or the potential difference across each of the circuit components, each of the resistor. This is how we measure the voltage. So the voltages are different. So the point here, if I want to measure the voltage here, or what you call the EMF, the electromotive force, I will have to connect a voltmeter also parallel to the battery. I have to connect a voltmeter parallel to the battery, which is V total actually, which is V total because it's the total voltage. Okay, so if every time or any time we want the voltage across the battery, we have to connect a voltmeter also across the battery. But if we want the voltage across this, or what we call the PD, it is this voltage across each of these components that we call the PD. It is this voltage across each of these components, circuit components, that we call the PD. The voltage across this resistor R1 and R2, they are called the PD. But the voltage across the battery or the power source, the voltage across the battery or the power source is what we call the EMF. Is what we call the EMF. So I hope this concept is clear now going forward. So you need it in order to be able to solve problems, to be able to differentiate questions, especially multiple choice. Now let's move on quickly. So now we're saying that the potential difference is the work done by unit charge passing through a component. The work done when a charge passes through a component. You can see, for example, you can see we have a total EMF of supply from the battery of 12 volts, a voltage of 12 being supplied by the battery. Now this voltage, when measured across this bulb, the voltage here, when measured in parallel, if you connect the voltmeter in parallel, remember we mentioned that voltmeter is for measuring voltages. If you connect the voltmeter in parallel to this bulb, this is a bulb. So we see that the voltage across this bulb is 5 volts. If you connect a voltmeter across this resistor, this is the symbol of a resistor. Okay, if you connect a voltmeter across this resistor, you see that the voltage here is 7 volts. You remember the total must be 12. The total across these two components or any number of components must be equal to the total in the power source. So 5 plus 7 has to be 12. Okay, so the potential difference is the difference in the electrical potential across each component. So the difference in the electrical potential across each component is called the potential difference. So in the case of a bulb, we have 5 volts as the difference in the potential across the two terminals when you connect a voltmeter in parallel to this bulb. And in the case of resistor, it's 7 when we connect across this. So we say the definition of a PD is simply the energy across the component, which is work done on energy that is transferred divided by charge. Okay, so it's same thing. Now here is another question. We've told you, or we've given the symbols for each. Potential difference is volt, is V, and W is the energy transfer or the work that is done, okay, to the component from the charge carrier, the work, the energy transfer to the component from the charge carriers, and it's in joules. The energy is always in joule. And then Q is the charge on each charge carrier. Now in circuit, the charge carriers are what? Electrons. What carries the charge? Because the charge, the positive charge do not move. The positive charge do not move. So what carries the charge? What moves is the electrons. So electron carry the charge and move them around the circuit. The electrons, they carry the charge and move them around in the circuit. So the tutorial has already explained this. Okay, so this equation can be compared or should be compared to the definition of EMF. If you look at these two equations, it's similar or it's same to that of the EMF that we've described. Now let's take a look at the question we have here on potential difference. It says, from the unit below, select the appropriate unit to measure the potential difference. The appropriate unit for potential difference is also volt. Remember the EMF, the voltage, and potential difference, they all have the same unit called the volt. Okay? Okay, now let's move on quickly. Measuring potential difference. How do you measure the potential difference? We say we use an instrument called the voltmeter. We use an instrument called the voltmeter to measure the difference in potential across two terminals in a circuit. So the potential difference is measured with what? An instrument called the voltmeter. So we say voltmeter is used for measuring the potential difference. Voltmeter. Voltmeter is the instrument we use for measuring the potential difference. The PD or EMF or voltage. So we use voltmeter as the instrument to measure all of this. Okay, we use the voltmeter to measure all of this that we've described in this class. Okay, let's move on quickly. But however, this voltmeter, we have the analog one, we have the digital voltmeter. The analog one is the one that's calibrated, and when you connect across, you have to read the values yourself. We're going to see, I think, a sample of an analog voltmeter, this one. This is an analog voltmeter. So when you connect it in parallel, these are the wires that you connect across the terminal of the resistor or of the bulb. You just connect this one to one side of the bulb, and you connect one of the wire to one side of the bulb, and then the second wire to this other side of the bulb. It will now be in parallel. When you do that, you'll be in parallel. Okay? So the voltmeter will measure the voltage across the component or the voltage across the battery. So we have two types of voltmeter, like we said. We have a digital voltmeter, which is an electronic readout. When you connect a digital voltmeter, it will give you the value straight away. To tell you maybe it's 2 volt, 3 volt, 1.5 volt. It gives you the value straight away. You don't have to read the values like this, because this one you have to read. You have to calculate, okay, this is 2.8 volt. So you have to read and write down yourself the 2.8 volt. But a digital voltmeter will display the value, the exact value for you to just write. You don't have to start trying to read the numbers. The exact number will be displayed while using a digital voltmeter. So voltmeters are connected in parallel always with the components that is being tested. Both the component that is being tested and also the power source, the battery, which is the power source. So you connect the voltmeter in parallel to both the components that you're testing or the power source that you want to know how much voltage is in the power source. Now the potential difference is the difference in electrical potential between 2 points. We've already established this part, this fact. The difference in the potential between 2 points. Therefore, the voltmeter has to be connected to the 2 points in the circuit. We have to connect it to the 2 points in the circuit. Now, analog or digital, analog voltmeters, they're subject to parallax error. Okay, analog voltmeter, they're subjected to parallax error. This is a question from paper 6. Analog voltmeter, one of the problem is a parallax error. A parallax error is an error reading that is caused by not reading the measurement at eye level. There's no line of sight. You say in a corner or in a diagonal and you read something. You're not like your eye level must gauge straight, must be a line of sight, a straight line from your eye level to the object that you're measuring. For example, we can illustrate this one briefly, quickly. Okay, parallax error is, for example, if I have this calibration. Okay, let's say we have this. Here is 0, and here is 5. Here is 0. Here is 5. Here is 10. Here is 15. Okay, here is 20. Here is 25, and so on and so forth. Okay, let's say this is what we have. We want to read values here. And we've put an object here, and we're measuring from here to here. We're measuring this object. Okay, the eye level must be such that it's a straight line to avoid error due to parallax. The eye level must be a line of sight. Must be a line of sight. If this place is where you are measuring, like this place is where you are measuring, your eye level must be directly to this point. Must have a line of sight. Not like you come and stay here and your eye is here and you're measuring this object. You'll read this value. You're definitely going to get the value wrong. Or you stay this way, your eye level is this way. Okay, your eye level is this way, and you're reading an object that is here. So here, it's considered to be wrong. This is considered to be wrong. And the error that surmounts from here is called the error due to parallax. This is considered to be correct because you have the correct line of sight. And here is also considered to be wrong because the error here is called the error due to parallax, or the parallax error. So in most of the alternative to practical paper 6, they always ask you about the parallax error. Or you should always state that most of the mistakes are coming from error due to parallax. And then we also have the zero error. Most times, some people don't count from the zero. The zero error is the error when a measuring system gives false reading when the true value of the measured quantity is 0. The zero error is the wrong reading that the instrument gives you when the true value is 0. So we call that the zero error. The zero error is one of also the problem that comes from the instrument itself during measurement. Okay, so this is how to connect. If you want to measure the voltage across this resistor, you connect the voltmeter in parallel to this resistor. This is how we connect the voltmeter. Okay, so with this we've come to the end of the first section. And if you want to connect across this one and the bulb, you also connect the voltmeter across this bulb, parallel to the bulb. Okay, so with this we come to the end of the first section. Our next class will be on resistance. Okay, resistance. We'll do resistors, the total resistors in circuit, how to calculate resistors in series and resistors in parallel, and so on and so forth. Okay, so with this, we come to the end of this session. Thank you for joining us.